This following circuit diagram is focused on band reject filter, and this can be found in the notes linked below the like button in section 14.5. For the parts that we're looking for, we're calculating and finding, we're going to be looking at the formulas on page approximately 124. We see that the notes provide a very similar example, and even if it was a little bit different, we would just change some things around. We need to calculate our omega naught. To calculate the omega naught, we're also doing it in kilorads per second. We are going to set our omega naught equal to the square root of 1 over L times C. Now the L is the capacitor and the C is the, the L is the impedance and C is capacitance. So we're going to take the square root of 1 divided by the parenthesis 625 times 10 to the negative 6 for micro, and then times 25 times 10 to the negative 12 for the pico. And then we are going to get a pretty big number. And what we're going to have to do is multiply this by 10 to the negative cubed to get it to be in kilo. And if we do this, we are going to get that our omega naught is approximately, or not approximately, it actually is exactly 8,000 kilorads per second. So the number that this is going to give us is going to look like this, and we just move the decimal 3 over, and that'll give us 8,000. For F naught, all we're going to do is take our omega naught and plug it in here, because we know that omega is equal to 2 pi times F. So we can write this as 8,000 as our omega divided by 2 pi is equal to F. And if we plug this into a calculator, we're going to get 1273. Now we need to find Q. And Q can be found two different ways. Q can be found if we have our omega naught over our beta. We don't have our beta yet, so the second way we can find it is if we change this around, plug something in, and we're going to get the R squared times C divided by L. Now if we plug our R squared, which is this resistor, our capacitance, and then our inductor in here, we are going to get a Q of 16. Now we need to find our omega C1 and then our omega C2. So these are the lower and upper parts, and for these we are going to use the formula that can be found in the notes. These are linked below the like button, and they look like this. So we would need to, the only difference between these, the omega C1, the lower, is that we have a negative, and the omega C2, we have a positive. And so we would plug in our R, we would plug in our C, we plug in our inductance, we plug in to these two equations, whatever numbers you have for your inductor, your capacitor, your inductor, and your resistor. And you plug those in respectively. And then from this, you're going to get approximately 7,750 for this problem, and then 8,250 kilorads here. Now we need to find beta, and beta can also be found two different ways. So beta can be found when we have our omega C2 minus our omega C1, and then this is also equal to a 1 over R times C. Now I prefer this way when we have our omega C2 and our omega C1, and this is because this problem is asking for it in kilohertz. Now if we were to do it like this, we would get rads per second. Now even doing this, we get rads per second because we have this omega C2 minus our omega C1. So we are subtracting radians here, but radians is in rad per second, and the question is asking for us in hertz. Well, hertz is frequency. So what we can do is take our 8,250 minus our 7,750, and this is going to give us a beta equal to 500. Now, make no mistake, this is in rads per second. We need to convert this into frequency. So this is going to become and we're going to use this formula right here. We have omega equal to 2 pi f. It's going to become 500 divided by 2 pi, and that's equal to f. If we do this, we're going to get approximately 80 kilohertz for our beta. That's how you go about looking at this problem. It's a band reject filter in parallel form.